Okay, so now I'll kind of give you more of a definition for what a recurrence relation is. What it does is it defines the nth term in terms of the previous terms. That could be like we saw above, where we defined our next term as n times the previous term, right? So that was an example where it was defined just in terms of the one before. You can actually have recurrence relations where it's defined in terms of the two before, or the three before, or actually in terms of all the previous values. The recurrence relation and the ideas with a recurrence relation do require initial ideas, initial values. So as an example, you use this in computer science when you sometimes define something recursively. Like, for example, maybe your computer language doesn't support an exponent. Let's just pretend that it doesn't. Uh, so we might pass in to our exponent function uh, x, and we want to raise it to the power. So this is the thing we want to raise, and this is the power. Let's assume here that we're limiting our exponent function to just positive values. So what this would do is it would come in and there would actually be basically two situations here. If n is greater than 1, then we would do exp of x. So exp of x and n. We would start off, we would say if n is greater than 1, then do exp of x and n minus 1. So what that does is it calls the function again. And programmers use this, so it'll just keep calling that until we get to the case where n is equal to 1. And then we would just say, when that happens, return the value x. So, let's see if I'm saying this right. I missed something here. So if n is greater than 1, what we would do is we would say x times exp of x n minus 1. Right, that's what x to the n would be. And then it would look up this thing. So it would do n minus 2, n minus 2, eventually until it get down to if n is equal to 1, then we would just return the x value. So it would come back, return x, then it would come up to for x squared, and it would do x times x. That would give you an answer. Send that back. Then it would do x times x times x, and so on. And so that's how you could actually recursively define an exponent. You can actually recursively define an exponent that way. And the nice thing is the computer does all of that in memory, and it doesn't have to keep storing a whole bunch of stuff. It doesn't have to keep storing a whole bunch of stuff. And that's a very common idea with a recursive function. So that's just an example with an exponent. So let's see some examples here of some recursive functions. We're going to say here, in this example, we want to list the first 7 terms of the sequence. So let's look at our first example here. Let's say that an is defined to be 1/3 times an minus 1. So it's 1/3 of the previous value. And let's say that we're told the initial information, a1 equals 2. You see, when you have a formula here like this, it's defined in terms of a previous value. Then we need a base starting point. So this problem here requires just a single initial value because there was only expressed in terms of one thing. If your function was expressed in terms of like an minus 1 and the one before that, the 2 terms before it, right, the 2 terms before it, then you actually would have 2 initial declarations. We'll see that in a moment in our next example. But let's look at this one here. So A1, of course, would just be itself, 2. A2 would be 1/3 of that. So 2/3. A3 would be 1/3 of 2/3. So 2/9. A4 would be 1/3 of that. 2/27. A5 would be 1/3 of that. 2/81. A6 would be 1/3 of that. 2/243. And finally, A7 would be 1/3 of that. 2/729. So we can look at the terms here. And in this example, with this recurrence relation, you might actually be able to say, hey, you know what? I can actually come up with a formula here for this, right? I can actually come up with a formula here, right? It's just 2/3 to the 1 power smaller than it, so 3 to the n-1, right? It's actually just 2/3 to the n-1, right? Of course, when n is 1, that would be 2/3 to the 0, which would be 2. When n is 2, that would be 2/3 to the 2-1, which would be 2/3. And for 3, it would be over 2 squared, over 2 cubed, and so on and so on. So some recurrence relations you could actually get into a formula pretty easily, and this was definitely an example of that.